So quantum mechanics is seriously weird. These things behave like waves when you're not looking, in privacy all the way by themselves, and as soon as you look up, suddenly it's a particle. But how's that going to help us with white dwarfs? Let's get back to some astrophysics now. The idea of this quantum mechanics is it can help us allow this white dwarf Sirius B to withstand its immense pressure. How's that going to work?
Well, I think it really comes down to quantum mechanics is even weirder than what we've already told you, because there are some other rules that are very counterintuitive. So when you look at, for example, a hydrogen atom, these are the different places, the little energy levels that an electron can be around a hydrogen atom. But there's a rule that chemists have figured out for atoms heavier than hydrogen that have multiple electrons, is that the electrons do not like to be in the same state at the same time. This is known as the Pauli exclusion principle. And so, for example, if this were, for example, the ground state of iron, you might expect all of its 26 electrons to pile down right next in the lowest energy state. But it's not allowed to do that. Indeed, it's only, one atom in each state, and so they end up having to distribute themselves through all the different levels. And that turns out to give you a set of rules that means that you can't push things together very closely.
Yep, so the Pauli exclusion principle says that particles called fermions, which includes quarks and hence neutrons and protons and electrons, can only have one energy state. It actually goes right down to some fundamental symmetry in their nature. There are other particles that can pile up in the same energy state, like photons, for example. But the fermions can't, which, as every chemist knows, tells you start filling up the energy levels from the bottom and so up. It's interesting to think if electrons had not obeyed that rule, then everything would be in the ground state and everything would be chemically like hydrogen.
Right.
And so it wouldn't be possible to have life. Hydrogen can't do anything like the richness of bonding or something like carbon.
But it would be so much easier to calculate.
Chemistry would be so easy.
Yes, that's right.
But luckily for the existence of life, there is this Pauli exclusion principle and things can't all sit in the lowest energy state. But then there's a second clue, which is called the Heisenberg uncertainty principle. Now, P here is momentum. What it's telling us in X's position, what it's telling us is if you have an uncertainty in the position and an uncertainty in the momentum, multiply them together, it must be more than h bar on 2. H bar is Planck's constant divided by 2 pi. So what this is telling you is when you confine an atom to a very small space, its momentum becomes highly uncertain.
Right, so if I can go through and say the uncertainty in the position is tiny, then I'd end up not knowing much at all about its, its momentum and usually velocity, but mass.
This is a generic thing about waves. So if you think about it, if you've got a wave and you compress it into a small space, it must have a very short wavelength. So a short wavelength means lots of energy, so it's going to be moving like crazy. In some sense, this is actually what drives diffraction in telescopes we talked about in the previous course. If you have a wave going through a narrow aperture in a telescope, it bends out a lot. It's got quite a lot of momentum. If you have a wide aperture, it bends out less. So these are the two clues that are going to allow us to work out why white dwarfs like Sirius B can survive. The Heisenberg uncertainty principle and the Pauli exclusion principle. So let's look at that.